All right, let's get things started. It is my great pleasure to welcome my dear friend from many years, Dr. Rajeev Shorey. Rajeev is most recently at the Indian Institute of Technology in Delhi, and he's leading a cross-university collaboration. In his previous incarnations, actually till quite recently, he was at TCS, the largest software company in India. And he's held many very high-level managerial technical leadership positions in various companies in India, IBM Research, Sasken, TCS, GM. And he's particularly well known for starting, and now he's the chair of the steering committee of this conference in India called Comsnets, which is probably the most well-established, most well-known conference in the Indian conference calendar. It happens in Bangalore every year in the same hotel. It's got the best reception of any conference that I know of, and the who's who of the Indian software industry, from starting people to CEOs show up at this conference. And academics from all the IITs, from IISc, they show up. So it's just a great experience. I've had the opportunity of being there several times, of really meeting in one place the who's who from the software industry and from academia. Most recently, he's also started another conference, AIMLSystems. He's going to tell us today about some technical work on federated learning. And he said he wants this to be interactive. So while the talk is going on, feel free to stop him with comments and questions. Yeah. All right, take it away, Rajeev.
Thank you so much. Thank you so much. So let me at the outset, not as a formality, but as something that is a great pleasure, express my sincere gratitude and sincere thanks to Saurabh, Shumali. Great pleasure to meet you. It's a great pleasure to have a old friend, Vijay Raghunathan, again known like Saurabh for many years now. Vijay was serving as general chair of Comsnets 2 years ago. And we used to interact a lot. Vijay is now getting back now. So a great pleasure. Thanks, Shumali. Thanks, Saurabh, for your very kind hospitality and all the running around. Really appreciate your efforts and your time. We look forward to reciprocating this in India when you're there. Also invite colleagues in this room to try to spend time and attend the Comsnets conference. Now probably the only conference that side supported by both ITB and ACM, and also the new AI system conference. So let me go straight. Also, I'm glad to be back in Purdue after 3 years. I used to be coming here at least twice a year. Minimum, at least once a year. With my former colleagues. So it's an added pleasure to be back here after 3 years. All right. So we're going to skip that. Let me just come straight to the topic. I think I was telling Saurabh a bit concerned because I have a lot to cover. These are some very interesting results that we have, in the last 6 months to last 12 months. So they're kind of fairly recent, but a lot of this is work in progress. So
Raji, one interruption. People are on Zoom are requesting if you can share your screen.
I see. Sorry about that.
Do you need help in doing that?
Sorry about that. Just give me a moment. Sorry, I should have done that earlier, but it's okay. Okay, can they see the screen now?
Yes.
Yeah, all set? Okay?
Yes, thank you.
Okay, so thanks Saurabh for reminding that. I'm sorry about that. Okay, so here's the agenda of my talk. I will very quickly motivate the problem. There's a lot of interest on Edge, and I think many of you are working on Edge. I do know that Vijay, Saurabh, Shumali, many of you are working on edge computing. And I think we all know the reason why it's becoming more and more important. But I think more specifically, there is a lot of excitement in federated learning and paradigms around it. It's not just federated learning, but there are many other things. For example, we're also looking at multi-agent reinforcement learning of late. And there's a lot of learning over there, right? And figuring out what are the right use cases is always a challenge. So I think the interesting question that we would try to ask ourselves going back 1 year ago with students was, listen, we all know federated learning, and of course, I'll give you an overview of what federated learning is. But what's the performance of federated learning, right? Everybody's talking about this, but do we know some performance figures? Can we get some results, not just through Python and its subsidiary, but its library, but can we get some results on an actual platform, right? For example, Raspberry Pi or something related around something, right? a kind of simple prototype. And so I'll be happy to share with you, some of the results that we have in the last 6 months to 1 year. So my talk is going to be primarily covering federated learning at the edge nodes. Now, as I said, as I mentioned earlier to Saurabh and Shumali, these are some recent results, okay? And I think these are exciting results where there's a lot of learning for us in the last 1 year. I will also quickly, in the end of my talk, because I thought, coming here, it's also good to share with colleagues here what else is going on. There's also some very interesting work going on in the academia and also industry. And how do you run a deep neural network on an edge device, right? Because edge devices, as we know, it's not the server, it's not the cloud, right? These are resource constrained. These are fairly limited. I remember the good old days in General Motors, where we used to do everything on that time it wasn't called edge, but it was called the compute platform. And everything had to be done there, including elliptic curve cryptography. So we are now seeing all this happening in the other world, the non-automotive world, right? So a lot of interesting stuff on how do you enhance the performance of deep neural networks on a resource constrained edge device. And that'll be my probably the last 10 minutes of my talk, because I'm going to really focus on part one. And of course, in every slide of mine, or at the end of every part, I will talk about the future research directions and open problems, because I think this is a very open space, and I'm sure that a lot of you here will pick up the threads and then extend that, right? So I think there's a lot of work that needs to be done in this space. I have to start with acknowledging my I'm very glad to work with some brilliant students. Manupriya has just joined Carnegie Mellon. She was with me for the last 1 year. Pavas Goyal is one of the toppers of the country, actually. I'm so happy that he's my student. He's joined this company called Graviton. And by the way, his claim to fame is that he's got the highest salary in India. So when I asked him, Pavas, what are you going to do with that $200,000? He smiled and he said, maybe I'll sponsor the conferences that we all run. So it's a joke, these guys are really making big bucks sitting in India. The game has really changed now. So Pavas is one of the sharpest students I've met, I've guided them many long time. I'm currently guiding Saurabh and Manav, who are finally a BTech CSC in IIT Delhi. I also work with some, very exciting students who are on top of prototyping. We realize that prototyping is something that is very critical now in any work in AI, ML, or in distributed systems. And so Tanmay, Avnish, Ishan, Anirudh are in the Delhi Technological University. I do work with Rohit, who's a good friend in Intel Research. He was in Cambridge as a postdoc. He's from IIT Kharagpur, the student of Sandeep Chakravarti. And you met him at Comsnet. And of course, Professor Huzur Saran, who's my colleague in the CS department. But I think great to have these students, and the pipeline is really full. Let me start and come straight to the point. Now, I think we all know what 5G is about. I'm not going to spend more than a minute on this slide, right? So 5G is really a plethora of technologies, services. The three key services in 5G, the three categories of 5G, as we all know, are enhanced mobile broadband, mission critical services, and massive IoT, right? So I think that's very well known. But what's interesting also is that 5G sounds great, right? I mean, it's a huge ocean out there, but there are many technology enablers in 5G. And one of the key enablers in 5G, there are many, right? There's millimeter wave communications, there's all kinds of technology enablers. But one of the very important enablers that are keeping us busy is the edge computing enabler, the edge paradigm, right? And we all know what that is. Why is this important? Well, for real-time applications, such as the ones, so people keep asking, what are the killer apps that you're talking about? Take, for example, automotive sector, right? Take, for example, a smart car. These are really real-time applications. You can't afford to wait beyond even tens of milliseconds. Even that could be fairly large. 100 milliseconds is an upper bound over there, right? In JSRC context. So if you look at the real-time application, this is playing a very important role, the edge nodes, because you really don't have time to go all the way to the back-end cloud. The latencies could be phenomenal, and you really cannot afford the latencies in real-time applications, such as industrial IoT that many of you work on, and automotive sector. And that's just two examples of many other examples, right? So we're seeing that this is becoming more and more important, the layer over here, but also observe that on a flip side, this does not have much resources, which cloud does, right? So cloud is like a whale, we call it a whale. There's everything is sitting on the cloud, right? Whether it's your ML algorithm, whether it's all your big data analytics, you just name anything and sitting on the cloud. But how do you get that over here and ensure that the performance is superior? So keep asking this question. With all the constraints that you satisfy, the performance has to be superior, whether it's latency or packet drops or throughput or cybersecurity or whatever. We'll talk about that, right? So therefore, this is becoming a very important, playing a very key role in 5G and even 6G going forward. Let's now zoom in. So I'm going to zoom in, as we talk. Let's look at what is federated learning and why faulty edge, because any work that does not include node, the faults in the nodes, the edge node, and I'm going to only focus on edge nodes now, right? So when I say nodes, I mean edge nodes. It's not the cloud. It's not the servers, right? The end servers. So it turns out that when the nodes fail, which is a very realistic scenario, then you really have to revisit the performance and figure out what do you do, how do you salvage, how do you mitigate? Because if you don't propose schemes, then it really becomes a work in its infancy. So you really have to figure out how to mitigate when there is a fault at the edge, and we'll figure out what that fault is. Now, again, I like to remind the colleagues here that this is work in progress. A lot of the results, as I talk to you, we are looking at results and extending a lot of work that I'm presenting today in the next 45 to 50 minutes. Okay, I will be happy to take any questions at the end of my talk, but if you have any compelling questions in between, I'll be very happy to answer your questions. Let's start with what is federated learning. And I'm going to request you to focus. So the slide now and the next slide are very important because rest all is really follows from what I'm going to summarize in these two slides. So let's look at this slide carefully, right? So you have a central server. You may say, why central server? Well, listen, let's start with something simple. You can't have a problem with complexity, right? In the beginning at t is equal to 0. So we have a central server. We have k number of edge nodes. Remind you all that these are edge nodes, okay? We're only focusing on the edge paradigm. So they're k edge nodes. And the way this works is, so a lot of my colleagues, we had this brainstorming session and look at this nothing but distributed system. Well, it's an old wine in a new bottle, but it turns out that the new bottle is a machine learning enabled by machine learning. So it's an old wine in a new bottle, but in a different context, and that context is machine learning. So let's look at some details now. So what we do is that the central server shares. So one of the important objectives of federated learning is privacy preserving. It's a privacy preserving paradigm. That is crucial. Because if you don't have privacy preserving, if that is not your objective, then you don't need federated learning, right? So we don't want to share data with anyone. You really want to keep your data. And I think I've given examples of many use cases where you don't want to share your data. Healthcare is one of them, right? Although it's not properly real time. But there are other nuances. So you want to keep the data with you at the edge node, but then how do you train the model? So, well, what the central server does is it shares a model with the edge node. So that's the step number one. It shares a model with actually all the nodes. So I'm talking, by the way, my assumption is a synchronous communication right now. So we talk about synchronous communication. There is work ongoing on asynchronous communication. So we'll come to that in a short while from now, right? So I share the model with the edge nodes. What happens is that recall that the local data is only at the edge node. It's never shared with anybody else, neither the peers nor the central node. And so what happens is I train that model, whatever be the model. It doesn't matter what the model. It could be a CNN. It could be any model, right? So irrespective of what the model is, now that's of course a work in progress. Because if you go from one model to another, each model has its own nuances, right? So doesn't matter, at this point in time, doesn't matter what the model is. So you train that model, you send the metadata back to the central server. For example, you send the weights, it could be other metadata, but typical example is you send the weights back to the model. Every edge node will do this, the same. This fellow at the central server will then aggregate. There's an aggregation algorithm there. You may ask, what is the algorithm? We'll come to that. Simplest is an average, right? You just take a simple average, right? And that's something what we call as a Fed average algorithm. So you now fuse not the data, but the weights from all the edge nodes. And then what happens is that this goes on, this iteration, you keep iterating these steps till you don't achieve a desired accuracy. So clearly accuracy is absolutely critical. And as you all know, machine learning is all about convergence time and accuracy, and we'll come to that in the next slide. So the accuracy is defined by the application or the use case of top. I probably am happy with 0.99 accuracy. I may be happy with 0.9 accuracy. I don't need 0.95 every time. Because remember, the price you're paying for a very high accuracy is that you'll take a longer time to converge. So there's always this trade-off, right? So as all of us know. So keeping that in mind, that privacy preserving is the critical, I won't say constraint, critical aspect of federated learning. I'm now going to share the model, and I get back the revised model, and I keep doing that till I converge. Okay, so that's point number one. Let's go to the next slide. But it turns out that this is a distributed system, right? I mean, federated learning is really running on a distributed system. Edge nodes are the K edge node, and central server is really a distributed system. And that distributed system is also characterized by its own parameters, right? And we know what the parameters are. So you have a network bandwidth from the central server to the edge nodes. You have a computation power. The assumption of heterogeneity, homogeneity is of course simplistic, but the nodes could be all very, in a realistic setting, very heterogeneous, right? So you have the computation power at each node, you have data volume. Now each node may have different data, different quantity of data, right? So it could be a D here, 2D there, 4D there, or whatever be the distribution of data, doesn't matter, right? And then of course you have the data skewness. You could have a very skewed data defined by a skewness matrix. We'll come to that, right? So you can use all kinds of definitions, right? Therefore, what you need to also ask is my federated learning performance, how is it influenced by these networking / system parameters? And that is important, because if you ignore all this, then it'll turn out that your proposed algorithm, which aggregates at the central server, may be a very naive algorithm, right? And you cannot ignore these parameters or metrics, the system parameters, system metrics. So I think that's another important point to note, that now you could of course add your own metric. Of course, it's not a complete list. You could have, for example, look at fairness in this system, and that also has many definitions, right? You can have another metric over here, maybe throughput or whatever, right? So that is of course something that is best left to what the application running on top is, what the application demands. All right. Okay. So having said that, let's move on and let's kind of look at some interesting results with that setting that I shared with you a short while ago. Let's look at some interesting results, and let's kind of you can figure out how these parameters influence my proposed the proposed mechanism at the centralized server. So just before we go into the results, the two key metrics, as all of you know in the work, that is in any machine learning work, is the accuracy and the convergence time. Of course, they're correlated. If I want a very high accuracy, it comes with a price, and that price is, well, I will probably take a higher, probably take a larger convergence time. If I want an accuracy which is lower, then I probably will get my results. I'll be happier much earlier. So it all depends upon what your trade-offs are, or what the trade-offs are coming from your application. One lesson we Hello. Yeah. Steps, right? Are we all set? All okay? Okay. Let me know if this, I can get a feedback. That'd be nice. Yeah. I don't know how much did they miss a lot? Okay, great. So just to recap, it's important to have diverse data sets. It's important to also work across diverse models, right? Now, why these models? There's no really, I mean, there's no mantra here, but it's just that these are fairly diverse models with its own characteristics, right? And it's important to get results with diverse models. Otherwise, it just doesn't, convince the reader that the work is really, works across diverse settings, right? So if you will. Okay, let's move on. Now, look, a lot of work that you read in the papers or from students is on the Python environment, PySwift environment. But it's very important to ensure that what you achieve or what you get from PySwift is also, that you have a prototype setup, howsoever simple, because otherwise it really doesn't go beyond the point. It doesn't convince the community that the results are indeed the right results, the validated, and so on. In some sense, this works as a validation of what you get from PySwift. So our work has both PySwift, of course, which is a given, right? But it also has a prototype setup. I'm not going to read all the lines over here, but it's a large number of Raspberry Pis with diverse, under diverse settings. So some fraction have a storage which is high, a fraction have a storage which is low. The aggregator, of course, remember the aggregator is the central server, right? So that works on a certain environment, and you could change that. Now, you could play around with all that. You could have all kinds of permutation combination, but it doesn't really matter. It shouldn't really matter, right? If you play around with these parameters, it shouldn't really matter. So long as your trend is similar and you get some interesting inference. All right. So with that, let's now try to answer certain fundamental questions. As I said, it's work in progress, but a lot of interesting results till date. So we'll ask some fundamental questions. The first question we are asking is, let's start with a very simple assumption of a homogeneous data distribution. All the edge nodes, right? So these are the edge nodes. So these are really into 100. So you're looking at 0 to 100, 1 to 100 edge nodes, and the data across all is homogeneous, right? Doesn't matter what your model is. Now, remember, these are typical curves. So whether it's AlexNet or whether it's ResNet or whether it's LeNet, and the list goes on and on, I'm just showing 3 at this point in time, you find that if you plot the convergence time, so of course you'll ask me what's the accuracy. Well, of course you define an accuracy, 0.95, for example. So given an accuracy, if you look at the convergence time versus the number of worker node, by the way, the edge nodes are called the worker nodes. So in literature, a lot of publications call them as worker nodes, right? Because they're kind of chugging, they're working on the model, and so that's really the worker node, right? You find that there is some W star. So the inference from this set of plots is there is some W star at which a convergence time is low. It's low. After that, it's increasing, and before that, it's increasing. So there is some W star where C, the convergence is low, right? Or it's minimal. Yeah, minimal. And doesn't matter what your data set is, irrespective whether it's MNIST or whether it's CIFAR 10, the trend is very similar. You will, of course, sometimes you have kind of, plots which are sawtooth pattern or ORI because, these are, by the way, average over 100 runs. So probably we needed more averages, but, we always are upper bounded by time. So sometimes you find, the results not the best results, but the key takeaway from these graphs is, the first takeaway is that number of worker nodes in your federated learning model is crucial, right? If you really want optimal number of worker nodes because you want a good performance, you don't need all the worker nodes. You need probably, just a minute, you probably can do with a smaller number of worker nodes, and that's true across, irrespective of what the model is. Yeah. This is the homogeneous environment. Just keep that in mind. Yeah.
When you say you have only one worker node, that means are you using the data from only one worker node, or you're putting all the data in one worker node? First one.
The data in one worker node.
Okay. So you're splitting the data among how many nodes?
It's a distributed system. The nodes are on the x-axis.
No. Okay. So I just want to make sure that the data that you use,
right,
when you say one worker node, is it the entire data on one worker node, or is it just the data split on that node you are using?
It's the entire data on that one worker node.
Then how is that different with the regular machine learning?
Oh, hold on.
So it's not really one. It's
No, hold on.
100.
The scale is into 100, right? Right. So what we are saying is there is some optimal number of worker nodes where convergence time is low. After that, it increases, and before that. So before that, it doesn't help you. You need at least right. So some W star, after which you're going to have a, it will flatten out, but you don't need to go. Look, you don't need to cover all the worker nodes. You're fine with a subset of worker nodes, right? It will probably change from one model to another, but that's the typical trend that you're seeing over here in a homogeneous setting. Yeah.
Kind of follow up on that.
Yeah.
What is the total number of real samples across all devices for each on the x-axis here? All 60,000 MNIST samples, no matter how many workers you have, there's 60,000 samples.
Yes, that's the MNIST data set, right? Yeah.
So that it's a little bit weird because what's changing is you're adding worker nodes, but you're keeping the amount of data the same. Is that true?
You're saying that we're adding the worker node, keeping the amount of data the same.
So are you giving like every worker node always gets 100 samples? Then as you add more worker nodes, you get more samples overall. Or are you saying I take my 60,000 and I split it depending on how many workers?
On the
They're very different settings.
Right, right.
So one is saying I'm increasing the number of total samples I have, and one is saying that each node gets more samples depending on how many workers.
It's the latter.
Yeah.
Total data split
Yeah,
among
you are
worker
splitting the data across all the worker nodes. Yeah, of course. Yeah, you're splitting. So the more the worker nodes, so let's say you have 10 versus 100, right? So in the first, you're splitting it across 10, and the other you're splitting across 100. You're splitting. It's a distributed system, right?
So the same
Yeah.
amount of data.
Yes.
Split
The total amount of data is the same, right? That is true.
And the worker nodes are identical. On that
Well, the
next.
worker node in this, to begin with, are identical, and the data distributions are completely identical. We'll complicate this now. We'll come to heterogeneity. We'll see some interesting inferences when the nodes are heterogeneous in terms of the data distribution. We'll come to that. But it's very simplistic setting. But interestingly, the trend is going to be the same. But look, it also depends upon how you define the heterogeneity. I'll come to that in just a few minutes from now. Okay. All right. So this is interesting. By the way, just a quick observation, and I'm sure you saw that. On the left is the MNIST, and on the right is the CIFAR 10, right? It's only because the scale is different. So, okay, and the x-axis is fairly clear. Let's go beyond this, okay? So let's look at the model accuracy and the convergence time, again with a homogeneous data distribution. So what's the observation from this? You find that as you plot for a typical model, right? For a typical model, whatever, I'll come to what the model is. If you look at the model accuracy and the percentage of worker nodes selected, these are the fraction of the worker nodes selected, right? You'll find that beyond some number, probably 60, right? In our investigation, 60, it's not sacrosanct, it's some number, some W star, which is 60 in this case. You find that the accuracy is fairly flat. Doesn't matter, you don't really have to go to 100. Fairly flat even at 60 or 65. So in some sense that suffices. If you look at the convergence time, then again you see that 60 is, as I said, a sacrosanct number. At that number, you find that the convergence time is the lowest in that function, right? Beyond that, it will increase, which you even saw earlier, and before that, it will increase. So there is some W star, which in this case happens to be 60, 65, whatever be the exact number, doesn't matter, where you have an accuracy, you achieve the highest accuracy, because beyond that, it's an overkill. You don't need that. And you have a fairly low convergence time, right? And that is around whatever, it's around some alpha percent, right? So A is almost similar to what it is at 100%. So you really don't need to spend so much of time and effort in going all the way to look at all the worker nodes, right? And so from now onwards, what we've done is in all the experiments, because remember, if you look at all the worker nodes and if you repeat all your results across diverse settings, which I'll come to, is going to take a humongous time. So it turns out that this number, whatever, as I said, alpha percent suffices for the worker nodes to contribute to the training process. You don't need to go all the way to 100. It happens to be 60, 65 in a homogeneous setting. All right. You may ask the question that, look, this number is a function of the model. Yes, of course. I'm giving you a typical result for a typical model. I think in this case, the model is CNN, n-layer CNN, whatever, 4-layer or 5-layer CNN. Okay. So of course the model is fixed. That's a given, right? So that's interesting. Now let's complicate the scenario, right?
Can I ask a question here?
Sure.
So I'm trying to understand this convergence time a little bit better. So is the trade-off that if you add more nodes, you can get more parallelism, but then then it doesn't converge as easily?
Right.
And so that's the trade-off.
Right.
Because it ideally, because I'm sure a centralized setting in some senses converges the fast, but it's not parallel. Is that the?
No, yeah, you're right. No, you're essentially right. You're exploiting more parallelism as you have more nodes. Yeah.
And so
It's a trade-off. Yes, it's a synchronous setting. Remember that. It's a synchronous setting. This is not an asynchronous setting. Yeah, it is all about you're getting more parallelism as you have more nodes. That is true.
But then I guess I'm slightly surprised that the accuracy is the highest with the most number of nodes.
Right. Yeah. Look, it does increase. But the delta is very small. And so the question is that when you are working across diverse parameters and system parameters and metrics, and you really want you really want to see how the system behaves, you don't want to spend so much time. It turns out that with this X% of the nodes, it suffices for you to get results going forward. So
I'm looking at that. I'm confused about, is this a fixed amount of time or something? Because I would think the centralized setting would have the best model accuracy, which would be on the left, right? A centralized setting would have the very best, right?
Right.
You can't expect better accuracy than centralized.
But that's a trade-off, right? I just said. Right.
So why is the left part of the graph going so far down? Are you fixing the time budget here? Is that why it goes down?
No, the accuracy, look, the more the nodes, you certainly go, I mean, intuitively you're going to have more and more accuracy, right? You're going to have number of average, you have more samples at the centralized node, right?
So this is different than the last setting in which you now have more samples. Total samples across all nodes is increasing.
Look, what we're saying is that if you look at the model accuracy, it's intuitive that if you have very low percentage of worker nodes, you'll have very pure accuracy because you really are averaging or whatever over a very small set, right?
So with the 10% number,
right,
90% of the data is not being used. Is that what's going on?
With the 10% of the worker nodes, you're finding that your convergence time is extremely high, right? Which is evident here. And
your accuracy is low because
it's taking
you're
a beating
not
there.
using 90% of the data.
Right. Yeah. And so these are the number of nodes. This is 50, 100, 200. But irrespective of what the number of nodes are, the trend is similar.
No, I thought the data is constant. The total
But
amount of
that's
data.
what David is
Yeah, I
getting.
think
at.
what-
This is different from the previous setting. This is different. Yeah.
We're trying to look at across diverse settings, right? So we're trying to revisit results. In fact, as you introduce heterogeneity, you'll find that. So I think one of the confusion probably is because the models are different, the settings are different. We just want to figure out the trends in the federated learning as far as the performance is concerned.
So Rajeev, can you clarify this one point? So let's say on the left plot, if you're looking at 20% worker node select, okay? So this means that the overall data has been split among all 100% of the worker nodes. And I'm only randomly selecting 20% of the worker.
At this point in time, it's random selection.
Okay. So then this clarifies, David.
At this point of time, it's a random selection. Because we will complicate that further when we look at some more intelligent ways to look at parameters such as bandwidth and volume and the other skewness and find that this changes.
Got it.
Right. This is a random setting.
The graph is kind of intuitive now. Like it's kind of trivial because you're adding more data.
So it is different from the setting in the previous slide.
Yeah.
I had a question about the model. Is it Fed average or Fed?
No, this is Fed average. This is all Fed average. At this point, it's all Fed average. I'm going to introduce a new model, which is Fed mitigation. It's called FF, Fed FF. At this point in time, it's a very simple model, the legacy model. This is all, yeah, thanks for pointing out. It's all Fed average.
What
Okay.
I was asking was there are theoretical results that say that as you increase the number of nodes in Fed average, the convergence time is worse because it's a higher probability that the nodes are going to diverge from centralized data.
Okay.
So is that the reason why you see that in the sweet spot?
Look, the Fed average is a very limited algorithm, right? It has its own limitation, and we all know why. So there is a need to extend that, and that's my next few slides. So let's kind of keep that, let's park that for the next few slides. Yeah, you'll see that one can do much better than the Fed average. Let's look at let's complicate the scenario. All right. So let's now plot the percentage of worker node versus convergence time for a given accuracy, and now you have a very heterogeneous data distribution. By the way, the heterogeneity here is a very simple heterogeneity, which means that as you go from, so let's say node 1 has a data D, I mean the volume, then you probably, so one of the assumptions was to have an arithmetic progression of data, right? So D, 2D, 3D, 4, so on and so forth. And as you increase the heterogeneity, right, you go from low to high, you can increase the common difference, right? So D becomes 2D and becomes 4D, right? So it's a very simple heterogeneity. What I'm just saying is that your data across different nodes is fairly different, right? Of course, there is a method behind that madness, which is the arithmetic progression. And now you see that as you increase the heterogeneity, this curve shifts on the right? Which really means that, and again, it's not surprising that as you have more and more heterogeneity in terms of data, you find that the converge. So what is our focus? Our focus is we want a low convergence time, right? But it's happening at higher percentage of worker node that you select. So the 60 or 65, that red, which was homogeneous, I kept mentioning 60, 65, doesn't matter what the exact number is, it is now moving towards around 70, 75, right? Not surprising, because now you need a larger number of worker nodes to arrive at a decision, because you really are working in a very heterogeneous setting, right? You may say that, well, it depends on how you define heterogeneity. Of course, yeah, it is going to be sensitive as how you define it. But for a given heterogeneity, low is, just have a very simple linear curve. High is, you have a fairly drastic buildup, and that's exactly how I defined it, right? So the minimal convergence time is shifting towards a higher percentage of worker nodes as the heterogeneity increases. And therefore, the key takeaway from this slide is that your degree of heterogeneity impacts the optimal number of worker nodes. I'm using the word optimal in a very loose setting. It's really not optimal. It's kind of close to optimal, right? Optimal word is a very strong word. Okay, so not surprising. So that's another key takeaway from this slide. So now I'm coming to the point that you raised there in the last bench, right? So now what we did was we said, look, let us now work across diverse data sets, but let's define a more realistic setting. Now, what is that realistic setting? The realistic setting is some kind of a metric. You can define your own metric, by the way. This is not sacrosanct. I repeat, the metric here is not sacrosanct. It's a heuristic. So I think the better word is the heuristic. So what is this metric? So define a metric which is a function of the bandwidth. Now, just hear me carefully. B is the bandwidth from the worker nodes, all are in the homogeneous setting, to the central server. P is the processing power at each worker node, and V is the volume at each worker node. I'm in the homogeneous setting right now, so these save across all. So B, P, and V, you define a metric, and this metric is called the S score. S score is low as the bandwidth is high, which is good, because when the bandwidth is higher, between all the IoT nodes, the worker nodes, and not IoT, the worker nodes and the central server, you go to have, it's better for your model, right? It's good for the convergence. If your processing power is higher, that's good, because you can process that voluminous data in a shorter time. And if the volume is high, if the volume V is high, then of course, there's a trade-off. It will take a longer time for you, but it's also good in terms of the model. I mean, larger volume is also good for the model, right? So some S metric, it's a heuristic, I repeat at this point in time. And if you now, so what we do is we define the S metric, and you then order this. So you look at the nodes, all the worker nodes, not all, the 60% of the worker node, because that's kind of some kind of optimality, right? Remember the 60%. For those 60% worker nodes, you define the S metric for each of the worker node. You order them, right? It's a monotone increasing or decreasing function. And you now plot training losses versus convergence time, and look at this. So something interesting is happening here. If you look at random selection, so this is a selection strategy. Let me repeat. I'm trying to choose the worker nodes a little bit more intelligently than in a naive random fashion or in a dumb fashion. So that the red is a naive random fashion. As you go to different curves, it's only bandwidth, only volume, only computational power. And if you look at the S-based metric, if you call it S-based selection metric, you find that the training loss is fairly low compared to all the other metrics. And what this tells you is that it's good to know the system parameters. It's good to kind of, define a metric which is a combination of all these. Now, what that combination? You can certainly have other, you can have other nonlinear metrics over here, but it's just that you are, as I said, these are heuristics which tell you the trend, right? It'll turn out that irrespective of what your data set is, whether it's IoT security, which we got from Kaggle or MNIST, or even CIFAR 10, which I've not shown here, you'll find that we're doing fairly well when you combine all these parameters in a nice manner. So that's kind of an observation that do not ignore the system metrics, because though they are important for a faster convergence of your ML model with a high accuracy. Right?
Question. So does this mean the amount of worker nodes you want to select, or the particular worker nodes you want to select? Because if they're homogeneous, then it's just a percentage of worker nodes.
They are
like I have 1,000 nodes. I'm going to just select 600 of them.
Mm-hmm.
And so is it just like the central server is randomly dropping 40?
How do you select of all the set that you have, the denominator? How do you choose the relevant worker nodes in a more realistic sense, in a realistic fashion? Right. This is for right now. This is all a homogeneous setting. I'll come to it.
In that case, S4 will be the same for all the nodes. So how is that different from random selection, right? Because S4 will be the same for all the nodes. It doesn't matter.
So you're saying that the bandwidth, so this is between the edge nodes and the server. This is the processing power. This is the volume.
All the nodes will look the same according to this score. So is this a selection criteria for the percentage, or for each, like which nodes?
No, it's a selection criteria for the number of nodes. How many? Which nodes of the entire set are you going to select? Right.
Percentage.
Which of the end nodes are you going to select? Right, with the fraction.
The fraction.
The fraction.
It's giving you the fraction of nodes.
Yeah.
So then how is it like just then doing, if all the nodes send you a model, you should drop 40% of them and average 60% of them.
Yeah, so to answer your question, this is clearly a heterogeneous setting. It's not homogeneous setting, because I have my B, P, and V which vary across each edge node. Yes, of course. This is a heterogeneous setting, of course. So that's the reason that if you look at the last plot, which was a heterogeneous plot, this plot set the tone for the next plot. So yeah, so
That makes sense. Yeah.
of course.
Okay, so now you select nodes based on
Right,
that.
of course, because otherwise you're right. Otherwise it's the same for across.
Right.
No, but that's the reason that I showed this last plot, because now we are complicating the scenario and we are saying, okay, now what happens when it's a vector of P, it's a vector of V, and it's a vector of.
But it's still homogeneous in the sense that the data is IID.
Good question, Saurabh. Good question. At this point of time, the data is IID. We will define a scenario in a short while from now when data is non-IID. Yes.
Device heterogeneity and data.
Yes. At this point, but the volume is different, right? So the volume is a very naive metric. At this point of time, the data is IID, but there is work, a lot of work happening now, defining what non-IID is, quote unquote. What is non-IID? How to define that? What are the metrics? We'll come to that. Probably my last.
So on the second slide,
This one?
yeah,
Yeah.
The IoT security data set.
Yeah.
I'm curious on some the random the red line. It seems to have a lower accuracy after the 200 seconds.
Yeah, this is no, I know. I mentioned that. See, this I think it's a function of how many runs you have. We have 100 runs. Probably that's not enough. There's a fairly large data set, so it's a function of that. So you will find that the trend is not perfect across all the data sets, But I think the takeaway from this slide is that the S-based strategy of selecting the node is a fairly interesting strategy. I use the word interesting strategy. I'm not saying it's the best strategy. You could have another strategy which captures more metrics and you find, oh, I do better. So, okay. So you're right. I mean, this is it's not a very neat plot, but that's also because it's a function of how many averages you take. As I said, it's 100 in all these plots, but probably if you go higher, you do that. Yeah, that's something that one can investigate. Sure. All right, let's quickly go to, look, let me now go to the question you asked, Fed average versus that. I'm going to skip this. Yeah, let me come straight to the key part. So this graph tells you that as you plot, okay, so in a realistic setting, you will have workers that fail, right? Fed average assumes all the workers are healthy and they're up and running. So remember, Fed average algorithm does not propose solutions when a fraction of nodes fail. It doesn't do that, right? So that's one answer to your question. Now, if you complicate that, and if you try to ask a question, what happened when nodes fail? Let's answer that question in the next 5 minutes. So the first plot that you see is, when I plot the number of contributing workers with the model accuracy, and by the way, the model, now you're asking what the model is. This is a MCNN model. I'll be happy to share the paper. It's a CNN with some N layers, I think 4 or 5 layers. The CNN with some N layers, a fixed model, right? And it doesn't matter what that model is. But you find that when you have no failure, which is a red plot, the accuracy is strictly greater than when you have failure. We'll define what that is, right? So we see a lower accuracy in the scenario where nodes fail. And what is the reason for that? Because those nodes may have some important data. They may have data that is crucial for the centralized server, but that data is gone. Now, what do you do? Until you don't propose a mitigation strategy, well, do you want to live with the low accuracy? No, let's not live with it. So accuracy will be low because you've lost some data, right? But let's now figure out what do you do? How do you retrieve it? Or what's a mitigation? Okay, so this then tells you, this then leads us to some interesting proposed algorithm, which is called FedFM. FM is the fault mitigation algorithm. I'm not going to read through all that, but it's fairly simple algorithm. I'm going to show the plots and it will convince you on the algorithm. I'll be happy to share the papers with you. But let me just recap. What we do is we compare now in the plots the Fed average versus Fed FM. And let me again recap. Fed FM is built over Fed average, with the difference, number one, that it takes into account the S metric, right? S metrics includes the network parameters, number one. Number two, it proposes mitigation. What happens when nodes fail? So just remember that in Fed average, when let's say 10 nodes out of 100 nodes fail, too bad. You just can't do anything. We say, okay, let's now look at the remaining 90 nodes. Let's choose the right number of nodes and let's kind of repeat that over with the S selection strategy. And you find that when you compare Fed average, which is the red curve, with Fed FM, which is the dashed line, you find that the model accuracy is at any convergence time, by and large, the model accuracy is strictly higher. It's strictly higher. There is a delta. There is a delta. It doesn't matter what convergence time is, that this Fed FM is doing better. The three plots here are with different failed worker nodes. So in the first plot, you have 20% worker nodes that fail. In the second, 40% worker nodes fail, and third, 60% worker nodes fail. The fourth plot is the actual prototype setup. So we just wanted to convince ourselves that when we actually run this on a Raspberry Pi environment, not too many, but 8 at this point in time, the trends are similar. It turns out that the trends are similar. And the one key takeaway is that the fault mitigation is crucial for any federated learning algorithm. Otherwise, you just sit back and relax and say, I'm too bad. I really can't do much about accuracy. But the point is that you can do something about it if you intelligently do things at the centralized server. Number one, yeah, just give me a minute. With Fed FM, as you can see, we are able to improve the convergence time and the model accuracy, right, by and large. So now of course, it's not a large delta, but it is an improvement over the Fed average across all the diverse settings, irrespective of what the model is. Question.
So what is the fault mean every synchronization round some fail, or is it these nodes fail forever?
We just good question. We just the links are disabled. So we just take a fraction of the links from the centralized server to the node, and we just disable the links. So the nodes are not available.
For the whole time.
Of course, for the whole time.
Okay.
So there's a model, it's doing its work. and then you inject a link failure, and that implies node failure. So for us, good question. So it's really the link failure, which implies that I have no access to the node.
So like at some point in time, a link will, so some point during training,
Right.
a link will fail and that node is never, it's like a catastrophic failure.
It is catastrophic.
And that will happen throughout the process. Certain
Yes.
nodes will fail. And by the end,
Yeah.
20% of the
That's
nodes have failed.
Absolutely.
Completely.
That is correct. That is correct. So your the node failure is mimicked as a link failure, and you just so the question is what do you do now with the node failed? Well, you have the other nodes, and can you extract the best from the other nodes, the remaining n minus k nodes? Can you have a fairly good accuracy and a good low convergence time with the remaining nodes? So answer is yes, so long as you are using the S-based strategy, and so long as you are question.
Fed average is averaging all the remaining non-failed worker nodes, whereas Fed FM is averaging only 60% of the top nodes.
No. So this is of course in the same setting. Of course, you compare the same setting.
Same setting. And Fed FM, does that use the top 60% or it uses all the nodes?
Good question. Top 60% always. The entire results after my first two slides are top 60%.
Okay. Fed FM will take the top 60% based on S score. Fed average takes the average of all the non-failed nodes.
Right. Absolutely good. Yep. That is correct. If you now go beyond this and you see, if you now, again, it's a similar plot that you have no mitigation, the red line is no mitigation, and the Fed FM is the dashed line. It's just telling you that it doesn't matter what the scenario is, you do find that Fed FM is consistently doing well across various scenarios, whether it's different models or whether it's different heterogeneity and so on and so forth. So you really are able to intelligently select the remaining nodes so that your federated learning results are superior results vis-a-vis in comparison to the literature, which is Fed average. Of course, you have you have other Feds, but average is the naive that we are comparing. Okay, so by the way, these are the results with IoT security applications, and I thought that's important because remember that this is a very realistic data set. The data set has all these failures. You've captured the data where IoT nodes have not failure. The IoT nodes have all kinds of attacks, and you really want, so you have that access to that, and now you want to figure out in a distributed setting how can you converge very quickly while ensuring privacy, because remember in IoT you really want to ensure privacy. You don't want to share data with anybody else, right? So therefore for us, getting data sets which are more realistic, there could be others of course, is very important because it corroborates, it kind of supports the results with naive data sets. That's MNIST is very small. I agree that MNIST is one of the limitations, is a pretty small data set, but doesn't matter whether it's MNIST or CIFAR 10 or it's IoT security. Right. So that's an interesting observation. All right, and then just to conclude this part very quickly, and now we come to one of the questions that you asked. Now, what happens when you inject skewness, right?
So if I can interrupt for 1 second, I see we are at the 1 hour mark. So if anybody has to leave, by all means, we can leave. But we'll be here for another 25 minutes or so to wrap this up.
Yeah, I'm going to wrap this part very quickly because I really want to cover the non-IID part. And then you feel free to ask any question, but I'll have the second part. I'll take about 10 minutes with that. So it should be done in 10 minutes. Okay. So let's look at the skewness. Now, by the way, in the literature, the non-IID has many definitions, right? So you have all kinds of skewness. Now, by the way, this is a more realistic setting because you have dependencies and you have dependencies across worker nodes. You have all kinds of skewness. You can have attribute skewness, label skewness, temporal skewness, and of course, the naive quantity skewness. We started with a very simple naive skewness, which really means that not all classes have the same data size. Different classes have different data size, and simple to begin with. Now, if you look at the plots and you plot the convergence time versus accuracy, again, these are preliminary results. I'll tell you what we're doing now, and that's something interesting. You will find that irrespective of how many percentage of heterogeneous nodes, you see that, so 0 is no skewness, right? 0 is a blue line. There's no skewness, fairly high accuracy. It takes time, of course. It takes time to converge. That's a given. But if you inject skewness in your model, in your distributed system, not surprising that accuracy takes a big beating. It takes a big beating. Now, the work that we are currently looking at is, can you now incorporate So can you have different definitions of skewness? That's the first extension that we're working on. And the other thing is, can we now extend the S metric? So if you go back over here, right, can we extend this, enhance this significantly to capture nuances such as skewness in a more intelligent fashion? And that's what we're doing. So we do have a metric. We do have some interesting results, but I think this is pretty preliminary to show you those results because we've not taken averages over a large run. They just average over a small run because it takes a long time to get the convergence. So yes, interesting that in a realistic setting, you really need to, you have to be conscious of the fact that if I inject more skewness, and to your point, Shumali, and I have more and more heterogeneity, I have to be careful in federated learning. You may not achieve the accuracy that you want for a given application, given use case. So it's an interesting lesson learned with the data sets. This repeats across diverse models. The trend is similar. It doesn't change. Okay. So that's the key takeaway from this. So where are we now? So the key takeaway from these plots, as I said, we're still working on many of them, many of the extensions, is that it turns out the worker nodes play an integral part in the efficiency of the federated learning algorithm. You don't have to work with all the plethora of the 1,000 or 100 worker nodes. Remember, in real life, they're not just 100 or 10, there are many of them, right? Look at the IoT setting, right? So that's an important takeaway. Not all the nodes in the network are required for an efficient federated learning model. Maybe 60% is good in a homogeneous setting, but this 60% will become 70 in a heterogeneous setting, maybe more in a more skewed setting. So you're shifting the minima, the C min from 60 to 70 to even beyond, which really means that you will need more time to attain that A star that you need. And finally, we see that the FedFM does improve. Look, it's at every convergence time, it's doing better than the existing techniques because it employs fault mitigation. And so in that sense, it's kind of doing good, right? So a lot of work is going on in figuring out, can we compare with other techniques beyond Fed average? But there's really nothing else there out there. There's really nothing. It's still proposal, and it's not, we don't have any results for the other techniques other than Fed average. Okay, so that's the, let me quickly give you a peek. So now, what are we doing now? Some very interesting extensions. You could look at decentralized federated learning because, as we all know well, that the centralized server is a single point of failure. The question that we are asking is, if you now revisit this in a decentralized setting, is it feasible? Because now I have to, remember the good old literature of selecting the cluster head, right? So now you're going to select a server, a centralized server for a certain time delta t. How are you going to do it? What are the techniques? Is it going to be efficient? Is it going to work? So that'll have its own overheads. The other thing is a dynamic network architecture. Yeah, that's naive, that's trivial. How do you incorporate fairness? I mean, is fairness an important metric? I don't know. I'm not sure. Probably it is in a homogeneous setting. So how do you incorporate? What fairness are we talking about? Again, fairness has many definitions, right? There's proportional fairness, there's max min. I mean, what is fairness over here? I mean, is fairness important in federated learning? So we're just kind of asking ourselves that question. How do you investigate different definitions of skewness? There are many definitions. So by the way, one of the work we're doing is comparing distributions, right? Remember, we have to preserve the privacy. Can we compare distribution from one edge node to the other edge node? There are many mathematical techniques to do that, but figuring out, well, why should we do that? How will it help us? So that's something which is currently being discussed. And finally, one of the very important topics, how do you ensure that federated learning is secure? And that's something Shumali and Saurabh, and I think even Raghu, you will be working on, Vijay, that how do you, look, there'll be a large number of additional attack vectors because you can inject attacks in that setting where model weights are being exchanged. Now I can play around with that. So how do you, what are the additional attack vectors as federated learning becomes more and more pronounced and it's implemented by the community more and more? That's something which we are looking at. Not all, it's a huge attack vector set or attack surfaces, but let's look at some which are more relevant in the setting that I pointed out. So I think there's lots of scope for extending the work. It's going to keep many of us and probably all working, they get busy for a long, long time to come. So we submitted the earlier work to to an important journal that's awaiting. So some of the conferences, we published this in some of the conferences, but we are awaiting results from transactions. Let's hope that that goes through, and then we will submit the extended work later on. Okay, very quickly, let me move on to a very, I'll probably take 5 minutes. So the other thing we're looking at is how do you split, I'm going to skip all that. How do you split a very complicated model like a deep neural network? Let me rehash that. How do you run a complicated DNN on an edge server in an efficient manner? And one proposal is, let's split this fellow, split it somewhere over here, after some k layers of the n layers. So there are n layers, that's the breadth. We'll split it somewhere at the k layer. I'm going to run that split model over here. So k1 layers will be run at the edge, and the k2, remaining k2 will be running at the cloud, which is the server, right? Is that possible? How is the performance if you do that? And that's exactly what we try to answer. Okay, the problem is how do you split a CNN or any DNN, as a matter of fact, efficiently from between the edge and the cloud? And here is what we have done, right? So I'm going to skip all that. So what we do is that the first observation, so the 2 key metrics are the system latency. You want to minimize the latency. You want to minimize the end-to-end latency, right? Because it's a model being run on the edge, and you want to maximize the resource utilization on the edge. You really want the edge to keep busy. Otherwise, it's going to be idling. Utilization has to be pretty high, right? So remember, the 2 key metrics are system latency and the utilization at the edge. But in the recent work, we've also added energy, and that took a long time because it was a struggle to get the energy, to measure the energy at each Raspberry Pi, and with the model running on top, it was a nightmare. So I'm sure many of you are looking at energy, but we added a third metric, which is the energy metric, and defined an optimization problem. And I'll come to what we did. So here is what we did. Okay. So I repeat, we are splitting the CNNs from at the edge. So fraction runs at the edge, the remaining runs at the server. And the interesting observation, first observation was that where you split is absolutely critical. Look at the random splits. I don't know where random is here, but if you split the CNN randomly, just toss a coin or generate a random number, it's a disaster. It doesn't work. Not surprising, right? Because you have to split intelligently, and that intelligence depends upon how the model is. For example, your model could vary. So VGG16 is different from 19, and from AlexNet, from ResNet, from LeNet. So depending upon the model and its nuances, where you split the CNN at what layer is absolutely critical. And you can see that from these initial plots, right? You can see that I'm sorry, I didn't mention the y-axis is the total latency, and the x is the split point of the CNN, of the DNN. And you find that if you split randomly, you're in a bad shape, but you really want lower latency. So the first results for only latency, and then we add utilization energy. because you have to combine all the three together. It's an optimization problem, right? So not surprising that you have to split the CNN intelligently. How do you do that? The answer was from we define a optimization problem, not surprising at all for all working in resource optimization and networks. So you want to remember, this is, don't have to worry about what these numbers, what the variables are. This is the latency at the edge, transmission delays from the edge to the cloud, the latency at the cloud, normalized to whatever the parameters are. So this is the end-to-end latency, and this is the utilization that you really want to increase the utilization, right? So you want to minimize F1, you want to maximize F2. So you define a very simple F, which is F1, minimize F, which is F1, minus F2. You run this problem. The constraints are very simple. The total number of layers in the CNN, right? X1 is running at the edge, X2 is running at the server, right? And so you solve this problem. It's a multi-objective problem. Don't worry about all that. You're using all the parity efficient solutions. And then you find, so let's skip all that. That's not important. Let's go straight to the interesting results. You find that, right? You find that the proposed algorithm, which is the latency memory optimized splitting, so it's called LMOS, the latency memory optimized splitting, right? At the edge, does fairly well comparing to the other proposed schemes in the literature, existing schemes in the literature. This is, and we compared it with even degenerate cases when you run the entire CNN at the edge, when you run everything at the cloud, right? So these are all degenerate cases. So when you compare the latency memory optimized approach, you find that irrespective of what your model are, you're doing fairly well. And you can see that from these curves. So the latency is fairly low. Look at the left curve. Doesn't matter what the model is. And the utilization and the memory requirements is fairly low, the memory requirement, right? Comparing to the other approaches in the literature. And so now this is the third graph there, which I've not shown here because that's another work, which shows the energy expended. It turns out ELMOS is doing fairly well. Okay. And finally, if you compare even with other complicated models like MobileNet V2 or SqueezeNet, so this is our proposed approach. You are finding that ELMOS, it's not the best, but the accuracy is fairly high with the fairly low latency, right? As you compare with the other approach, it's been fairly well. Because again, not surprising, you're looking at the end-to-end latency, you're looking at the utilization, and in the extended work, we're also looking at the energy. Okay, so the key takeaway from this work, which is again ongoing, because we are trying to further run it on a mobile environment, and that's a challenge, right? As you all know, on an Android environment, because it's hard to optimize it, that the splitting is certainly a superior alternative for running CNNs at the edge. It does give you, I wouldn't say the best, but it gives you fairly good results. Vis-a-vis, if you were to run everything on the edge, it doesn't work. You will never get the latency that you want. Okay. All right. So as I said, energy has already been added. We could split on. Yeah. So one question that we've been asked always: well, did you look at multi-edge system? And the answer is no. This is only on one edge. So what happens when you have multiple edges sitting over there working? Something that we have to think about. We'll have to be looking at ELMOS on smartphones, and we could generalize this to other architecture like RNN, GAN. We're not looking at just simple CNN, which you saw, there were 4 CNNs, right? All right, so my last 2 slides, there are 2 important conferences that are now become very important in that side of the world, which is in Asia. We started AIMLSystems. This is the 2nd edition happening in Bangalore in October. So I actually rushed to Bangalore after I go back. But I'm pleased to share that the next AIMLSystem will be in US. First time we're bringing it to US. It will be in New Orleans or Baton Rouge. We'll figure that out. But it's clear, it's confirmed. And happy to share that some of the best minds in the globe in AI/ML are a part of the conference. So we'll be so happy to have our friend from Purdue to join the program committee. This has the top minds from all over US, Asia, Europe, and Australasia. So do see AIMLsystem.org. We're expecting about 20 speakers, and I don't know how we'll adjust, but it's getting to be humongous now. So it's a very interesting conference, which is supported by IEEE, ACM, and various institutions. And finally, all of you know Comsnets. Saurabh mentioned Comsnets. Vijay has been the former general chair. Saurabh is the keynote speaker in January. This is one of the top events in Asia now. Strongly recommend that you attend Comsnets in Jan. Every Jan, it's always in Bangalore. Attracts about 400 people. One of the most important conferences in that part of the world. So thanks to the committee and thanks to all the hard work that our great committee members put in and our local folks put in. I'm done.